Hi, good afternoon. My name is Matt Bandy. I'm with a company called Resi. And let me just begin by saying how sorry I am I couldn't be there with you this afternoon. I had an unavoidable medical procedure that conflicted, unfortunately. But I'm really excited to present this information to you guys on a full-scale test of a drone method that we implemented in early 2022 in a collaboration between Washington County, Utah, and my company, Resi. As some of you may know, we've been working on a drone survey method for tortoises for almost 3 years now. Here's a little information on the background to the project. In 2020, we began doing some experiments with styrotorts and detection of surrogates. In 2021, we did some initial data collection in the wild, as 'twere, or in the Pahrump region of Nevada, and at Armendariz Ranch with the Turner Endangered Species Fund's captive population of bolson tortoises, and at a couple of sites in Ivanpah, and we initiated discussions with the recovery office as well. Last year, though, was the first time we've really applied this method at a large scale in an actual regulatory context. And this was a large-scale test of the method on the Red Cliffs Desert Reserve, just outside of St. George, close to where you're standing now. We did about 5,000 acres, and we also did a test of the method using the Fish and Wildlife Service's styrotor arena near Las Vegas, which was very interesting as well. And that's what I'm going to talk to you about today. I might mention also that Resi has received a Marine Turtle Conservation Fund grant from the Fish and Wildlife Service to apply this method to do population counts of bolson tortoises in northern Mexico, and that's something we're going to be working on. We're going to be going into the field in a few months, actually. Just a quick refresher on the method. This is an object detection method using neural networks, or artificial intelligence as we often call it. The essential method is we tag a large number of images of tortoises in drone photographs. Then we train a neural network to detect the tortoises and burrows. I should mention that we have a burrow detection model as well. So we create two models, a burrow model and a tortoise model. The tortoise model is trained on a lot of images like this. Essentially about 500 images of this sort, largely Mojave Desert tortoises, some bolson tortoises as well. I should mention that we actually do try to include examples in the training data set of partially obscured animals, so ones that are partly under bushes or vegetation or in deep shade. And the model is actually pretty good at detecting these as well. So it's not just detecting tortoises that are out in the open. It detects them if they're partially under vegetation as well. And the burrow model is trained on about 700-800 examples of this sort of image. And the method, of course, is to simply fly a drone at a constant elevation over an area of interest. We found that 20 meters is the flight elevation that works best. And you photograph every square inch of that area and use the trained model to detect tortoises within that data set. The coverage is about a square mile a day and has the advantage that we don't need surface access at all. So the coverage rate is about 9 times walking speed and significantly cheaper as well. So the 2022 fieldwork that I'm going to talk about today consists of 4 components. First, we flew the Fish and Wildlife Service's styrotor training arena near Las Vegas, and that I'll present that first. Second, we did fund G-0 surveys in the Red Cliffs Desert Reserve near St. George to study surface activity. That was conducted by Ann McCluckey and her colleagues, and I'll talk about that second. Third, we conducted paired drone and pedestrian surveys of portions of Zone 6 of the Red Cliffs Desert Reserve, and then we conducted a drone survey of a portion of Zone 6 that prohibits pedestrian access. So a portion of the survey was conducted with both drones and pedestrians. A portion of the survey was conducted by drones alone. And all of this is a collaboration between a lot of entities. Resi, of course, Red Cliffs Desert Reserve, Washington County, provided funding and guidance and local expertise, obviously. The Fish and Wildlife Service was involved in the planning of this from the very beginning, Utah Ecological Services and the Recovery Office. We were also assisted by the Great Basin Institute and by the state of Utah. The first component, as I mentioned, were the flights of the Fish and Wildlife Services styrotor training arena. I flew these multiple times. For those of you who may not have been there, it consists of a set of pedestrian transects that are laid out over a landscape near Las Vegas. And tortoise surrogates are placed throughout this area. There are 144 tortoise surrogates placed, adult tortoise surrogates. The results basically are that we detected 233 of them, which is 81%, which is quite a good detection rate. It's higher than pedestrians normally. But almost more importantly, this was a method for us to test and to calibrate our analytical method that we use in wild populations or in uncontrolled situations. And what we use is a modification, a custom implementation of distance sampling to work with aerial photographic data sets. Essentially, it means that we're doing distance sampling with rectangular sampling areas rather than circular concentric sampling areas. So we have prepared an R package that implements this, and all of the analysis, the density abundance estimates, the confidence intervals that I'm going to present for the drone data, all were produced using this novel implementation of distance sampling. Here is a detection function for the adult tortoise surrogates that were detected at the training arena using drone distance, which is what we call the R package. And using drone distance also, we can calculate an estimated detection rate, G hat. So that is on the right-hand side there. We generate a probability density function of the detection rate, and you can see that the mean detection rate is about 80%, a little over 80%, between 80 and 83%, which, if you'll recall, is almost exactly the same as what we measured. Since we knew how many surrogates were out there, we could actually measure our detection rate, and it's encouraging to note that the estimated detection rate produced by drone distance, our R package, is very similar to the measured detection rate. And again, we flew the transect blocks twice. In the table here, it's block 1 and block 2. The charts give you a probability density function of our estimated abundance for each of those flights. And the blue line represents the actual known value. So, in block 1 and block 2, we both know that there are 144 surrogates present. Our estimates were about 147 and 148, so the overall error was about 1 to 2%. Very, very good results, very close to the actual measured counts, abundances, and detection rates. And again, just to show you a detection curve, the blue there is our detection curve based on adult surrogates in the arena. The red is the detection curve for the Fish and Wildlife Service's double observer method, which is used in their population monitoring program. So you can see the drone method actually produces higher detection rates out to further distances from the center line than does the double observer method, and much better results than the single observer method that we're familiar with from pre-project survey protocols and the like. So the second thing I'm going to talk about are the G0 surveys that were conducted by Anne McLucky and her colleagues during the period that we were doing surveys in Zone 6 of Red Cliffs Desert Reserve. These were conducted over 2 weeks, and in each of these cases, the surveyors recorded all the normal attributes that you would record on a G0 survey, including visibility to a pedestrian observer, but in addition they recorded visibility to a drone observer as well. So you can see that over this 2-week period, about 75% of the tortoises that were relocated would have been visible to pedestrian surveyors, and only 38% would have been visible to drone surveyors. So that is a pretty significant difference. And I think what's going on here is that we're seeing a difference in visibility based on time of day. So if you look at pedestrian versus drone visibility by time of day in the G sub 0 data set, on the left is the pedestrian visibility. You can see that the visibility remains pretty much constant throughout the day, right? You have a little dip in sort of the middle of the day, but it remains pretty constant throughout the day. It's very different for drones. So drone visibility is high in the morning, roughly comparable to pedestrian visibility, and very low in the afternoon. And what's happening is that the tortoises are retreating to their burrows, so they're more likely located just within the mouth of their burrows, not very deep, visible to a pedestrian, but not visible to the drone, or they're sheltering in vegetation and they're not visible to the drone. So this is a pretty significant result that came out of the G sub 0 surveys, and I'll return to its importance later. But for now, just remember that in the context of this wild population in Zone 6, tortoises in the afternoon are much less visible to drones than they are to pedestrians. So we're going to talk about the Zone 6 survey now. This happened just outside of St. George, just a few miles from where you are now. We did this in April of 2022, covering about 5,000 acres over the course of 2 weeks. And we surveyed a bunch of transects by both the drones and the pedestrian crews. And I should note that we did those transects on the same day. So the same day that the pedestrians surveyed a transect, it was also surveyed by drone. The pedestrian surveyors covered about 254 transect kilometers, and they detected 113 adults and 40 juveniles, as you can see on the map here. When we analyze that using conventional distance sampling, the distance program, we get an estimated abundance of about 411, with a confidence interval of 300 to 550, essentially. And pedestrian surveyors also noted when they encountered a tortoise, they noted whether it would have been visible to the drone or not, based on visibility from directly overhead, and they got the same result that the G sub 0 surveys produced. That is, drone visibility was quite good in the morning up until about 1 o'clock, and then after 1 o'clock it was very low. So we have two independent data sets that are giving us the same information. For the drone, we surveyed a total of about 27.6 square kilometers, including the transects that the pedestrians covered, plus a large block area to which pedestrians were not allowed access. This produced about 90 adult detections, 15 juvenile detections, and 2 carcasses. And just so you know what we're talking about, this is an example of one of the photographs. That little thing in the middle is in fact a tortoise that's feeding. So we have to analyze about 1 million of these photographs to find about 100 examples of tortoises. That's the challenge. Here are the estimated abundances for the three portions of the project, as we mentioned. And then when we compare the pedestrian versus drone estimates, we can see the drone estimate was about 300, the abundance estimate, as opposed to a little over 400 for the pedestrian, and the confidence intervals were accordingly lower. There's a couple of things to mention about that. So first of all, they did not produce the exact same estimated abundance or mean estimated abundance. However, the estimates do overlap significantly. The confidence intervals overlap significantly. So the difference in the means could be due simply to sampling error, right? It could be due to simple chance, or it could be due to observer effect. That is, it may be that the pedestrian, since we surveyed the transects on the same day with the pedestrian and drone surveys, it may be that pedestrian surveyor interaction with tortoises may have driven them to seek shelter, which reduced their subsequent visibility to the drone method. That's something we're probably going to need to test in the future. But regardless, the estimates are compatible, though the drone estimates do seem to be lower, the mean estimate at least. In terms of conclusions, I think we can say that the drone method is very successful at locating tortoises when they are available for detection, more successful than pedestrian surveyors, really. However, fewer tortoises are available for drone detection than are available for pedestrian detection in the course of the day, which leads to lower overall detection rates and to wider confidence intervals. I think we can address this problem by, one, by increasing survey acreage. We could just cover more territory or cover it multiple times perhaps. Or two, we can actually limit drone surveys to the morning or to the period from about 9 a.m. to 1 p.m., which we've shown to be the periods of greatest visibility for the drone method, which should go a long ways towards addressing that difference. The drone method has the advantage that it does not produce any surface disturbance. It's less than half the cost per square kilometer of pedestrian surveys. It can generate, using our drone distance R package, it can generate quantitative abundance estimates with confidence intervals. And we can also use it to document other resources. In this case, we did use it to study the dwarf bear poppy as well as the desert tortoise with very little additional cost. Thank you very much. As you can tell, we're excited about this. I really wish I could have been there to present this information in person and to discuss it. However, my co-author, Cameron, has agreed to address any questions that you may have. Thank you again, and please reach out if you're interested in talking about this more.